By God's permission, we will continue our discussion on MRI physics. God willing, today we will cover some aspects of the spin-echo sequence, and we will delve into it to maintain the same order. We won't discuss gradients today, but I will talk about the inversion recovery sequence, STIR, FLAIR, and FAT-SAT, which are saturation sequences. We will also discuss the magnetic transfer contrast. Last time, we started with, in the name of God, the most gracious, the most merciful. There is something very important you need to know when T1 sequences, T2 sequences, or proton density sequences occur. All of these fall under the umbrella of the spin-echo sequence. Why do we say spin-echo? Because the echo or signal that you are recording is based on the spin, relying on the application of a refocusing pulse, the 180-degree pulse, which then refocuses the protons, enhances the signal, and allows you to record this signal. And I have recording for this signal. T1, proton density, T2. We were talking about T1 with short TR and short TE. For T2, long TR and long TE. For proton density, it was long TR and short TE. Discussed why. I have a short TR, I have a short TE. I have a T2 long TR, long TE. I have proton density with long TR and short TE, and we discussed why that is. TR is considered a significant parameter for the T1 sequence, while the echo time, or TE, is considered a significant parameter for the T2 sequence. These are all spin-echo sequences, as we discussed. This is a T1 weighted image with different intensities that appear in my image. Of course, we mentioned that fat appears dark in T1, unlike water, which appears bright because the T1 constant for fat is shorter than that for water. As for the T2 sequence, we discussed that water appears bright while fat appears less bright. This is because the T2 signal, or transverse magnetization of water, still retains its value, which is higher than that of protons depending on the difference in proton patterns. We choose a long TR to minimize the effect of T1 and a short TE to minimize the effect of T2 under T1 conditions, and we select this for the T2. The signal will remain dependent on the final outcome, unlike those that depend on 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 those that depend. In this spin-echo sequence, we have the T1 image here showing a tumor, and around the tumor we see a part in T2 that appears white due to fluid, as we can see. In contrast, the CCF appears black, while the CCF is more bright here. This is also a T1 image, where the fat area appears more bright, unlike the cortex, which appears black in this way. Now, regarding the TR and TE values, if we talk about the T1 image, it ranges from 500 milliseconds for TR, while TE is from 15 to 20 milliseconds. For proton density, it is 2000 milliseconds with long TR, and for short TR, TE is 15 to 20 milliseconds. For T2, long TR is over 2000 milliseconds, while TE is 120 milliseconds. These are the values. Now, we discussed that I have a 90-degree pulse, and then I use a 180-degree pulse. We also talked about slice selection gradient, phase encoding gradient, and frequency encoding gradient, and we understood what each one does in special encoding. There is an important point we mentioned, that I give every signal a 90-degree pulse. I wait for half of the TE, then apply a 180-degree pulse, and after that I wait for another half of the TE and record the signal. Okay, we were saying that with each TR, with each signal or pulse I apply, I have the case of the signal. My data consists of lines from a case base, as we thoroughly discussed last time. Each row from the case base is completely filled. once at an angle, and each specific angle is filled. Accordingly, if I have 256, meaning I take 256, and my data is, of course, in milliseconds, let's say 500 milliseconds. So I have 256 times in total, and you decide your repetition time, TR. Now, if I really want to know how my scan time will be calculated, if I say 540, which is my TR, multiplied by 256, which is what I do every time, divided by 60,000 to convert from milliseconds to your scan time, it would be approximately 41 minutes in total. This is a significant amount of time. In order to reduce this time in the fast spin echo sequence, they said we will make use of a period called data time. This data time is the period between the recording time of the signal. You have data time 90 and then 180 to record your signal. After the first echo, in the first slice, there is a period that comes after the echo before you implement your repetition time TR. This period is a waiting time for the complete relaxation of your protons to return to their baseline state in the second slice. You cannot implement another RF pulse until complete relaxation occurs to start your cycle anew. So, in this case, we make use of this data time and implement another pulse. Basically, if there is another slice in a different line, at that moment, what have you done? You have utilized the space or time to perform a scan for more than one slice during a single TR. You can scan more than one slice, but in a different line. Here you will utilize the new space for slice 2 to provide another signal in the slice to fill slice 3. In this case, you are performing your scan because at that time you can scan more slices, your 18 slices that you worked on. You multiply them by 256 because during the single TR, you will fill one line from the case base for all your slices, your 18 slices. So you multiply it by 256, which is the number of lines present in the case base, and divide it by 60,000. You have 60,000 milliseconds, and to convert that, your time becomes 2.3. This is the technique used to reduce scan time. Now, there is something called fast spin echo. What is the fast spin echo? Instead of giving a 90-degree RF pulse, followed by a 180-degree RF pulse, I will record the signal after a certain time. After the first 180-degree RF pulse, what do? You wait until phasing occurs, and then give another 180-degree RF pulse, and after that, you record the signal. So, how will the shape look? You give a 90-degree RF pulse, then a 180-degree RF pulse, and then you record your signal. After that, you give another 180-degree RF pulse, and then record your signal again. This way, you have reduced your time after waiting and performing the repetition time. This sequence is called fast spin echo, and the number of 180-degree RF pulses is referred to as the echo train length. What is the problem with the echo training topic, guys? The problem is that if you increase too much, your signal, which was strong, when you received it, will weaken here. The amplitude of the signal will weaken, meaning that while you are applying it strongly, there can be a loss in the signal amplitude over time, requiring a 90-degree pulse reset. Therefore, you cannot prolong the repetition of the 180-degree pulse. This results in a loss in signal intensity or a loss in the signal-to-noise ratio. This is called fast spin echo. We can benefit from this by doing something called multi-sequence. Multi-sequence means that you give a 90-degree pulse and then a 180-degree pulse. At short echo time, you record an image and then give another 180-degree pulse to receive another image. This provides you with your T1 relaxation time information, And since this is long, it will give you an image along with the one you recorded initially. So you have managed to do that. With TTE and its sequences, you can perform multi-sequence imaging. In the same sequence, you get two images, one based on a short echo time and another based on a long echo time, along with your long repetition time. This results in T2 weighted imaging with your proton density in the same sequence, conventional spin echo, and fast spin echo. This is what happens with the repetition of 180-degram pulses. If it increases, you find that your signals decrease over time. Therefore, you notice that your signals diminish, and this continues to happen. That's why you will find that it has occurred at a certain point. The multi-echo or multi-echo imaging or multi-sequence captures a proton density image at short echo time and a T2 weighted imaging image at long echo time within the same repetition time. After 180 degrees, you record at the short echo time for proton density and at the long echo time for T2 weighted imaging. This is what happens. During this period, there is dephasing, and when you apply 180 degrees, rephasing occurs, followed by dephasing, again leading to a decrease. However, the signal amplitude here is high, and the amplitude decreases over time. So, if you increase your echo train length beyond the number of multiple 180-degree pulses, it will reduce the intensity of the signal. Our general feeling is that they are indeed actively working on it to meticulously fill it in this particular way. Okay. Certainly, it is important to recognize that no single solution can address every problem or challenge that arises. In many situations, a multifaceted approach is necessary to effectively tackle the complexities involved. This means considering various perspectives, evaluating different strategies, and being open to adapting plans as new information becomes available. For instance, when dealing with environmental issues, it is crucial to integrate scientific research, community engagement, and policy development to create sustainable solutions. Similarly, in the realm of technology, innovation must be balanced with ethical considerations and societal impact. By acknowledging the diverse factors at play, we can work towards more comprehensive and effective outcomes. A very large number of 180-degree pulses will weaken your signal over time. Now, I want to ask you a very simple question. Is fat considered to have a short T1 constant, meaning does the relaxation of fat return quickly or slowly? Quickly, while water takes longer. All right, okay, we have mentioned this. Nice. Why? Why does the fat take a bit more time? The T1 and T2 time constants for fat are considered to be faster than those for water, such as in medical imaging techniques like magnetic resonance imaging, MRI. In fact, fat and water are extremely important in MRI and play a crucial role in various diagnostic procedures, specifically because fat has a unique Ni and specific molecular structure, which consists of a chain of carbon E atoms. This chain can be saturated, meaning it has a certain number of hydrogen atoms attached to it, which is essential for understanding its properties and interactions with other molecules. The structure includes a carboxyl group, and the hydrogen atoms on this group are of particular interest to me because I am working on the protons present in fat. It has been found that the protons in water are indeed associated with two hydrogen atoms, and the hydrogen in fat behaves in a distinctly different manner. If you take some fat and some water and carefully place them in your magnetic field, you will find that their response to the magnetic field is not exactly the same. Why? Because the structure of fat is significantly heavier. Its molecules are consistently larger than those of water, which are small molecules that move very quickly. Additionally, the hydrogen present in fat is said to be in an environment where there is no magnetic field affecting the protons at all. Therefore, the protons in fat move at a speed or resonance frequency that is similar to or equal to the resonance frequency of the medium surrounding them. Two cars are moving at the same speed, and one driver reaches out to give a sandwich to the car next to them. Since they are moving at the same speed, energy transfer is facilitated. The same applies to the protons inside fat or lipids. They move at a speed similar to or equal to the protons in the surrounding lattice. Therefore, the spin lattice relaxation that occurs, or energy transfer, happens because it has already gained energy, and the loss of that energy to the medium is easier due to the matching speeds. This is why fat relaxes faster in T1 recovery. Dr. Islam, I'm sorry, but is there a Dr. Ahmed who could help with this? I'm sorry. I apologize, doctors, but let me repeat this part because it's important. Why are we talking about fat having a short T1 and water having a long T1? The issue, folks, is related to the structure. I'm not dealing with fat and water. I'm dealing with the hydrogen atoms present in fat and water. The hydrogen atoms inside fat and water respond differently to the external magnetic field. We all hear about the chemical shift. There is a chemical shift between water and fat, and there is even a chemical shift elevation. What is this chemical shift about? It's related to the structure of the hydrogen atom. It is a chain of carbon atoms, the structure of which belongs to fats, or a chain of carbon atoms ending with a carboxylic group, which is a double bond with oxygen. The hydrogen atoms present are a result of these carbon atoms being saturated. What does saturated mean? It means they are bonded and do not have electrons or charge. We always say that the magnetic field is related to charge. If you find any atom with a charge, you know that it has a magnetic field around it. Since the atoms have a magnetic field around them, they will be affected by and will affect the surrounding magnetic field. In the triglycerides, I refer to the hydrogen atoms present in this structure as shielded. What does shielded mean? It means they are not influenced by an internal magnetic field within their structure. The protons present in fats rotate at the same speed as the protons in the surrounding medium, which facilitates the transfer of these protons to the fats or the surrounding medium. This accelerates the process in fats. As a result, the heavy molecules have their motion facilitated in a manner that is significantly influenced by the bound molecules, which notably eases the energy transfer between the molecules. On the other hand, when talking about water, the oxygen is bonded to two hydrogen atoms, so its protons are particularly influenced by the oxygen, which has a negative charge. This negative charge creates a strong attraction for the protons due to the magnetic field produced around the oxygen, which has a higher effect on the protons, causing them to rotate faster than the protons present in fats in this scenario. As a result of the small water molecules moving extremely quickly, there is a significant mismatch in the resonance speed of the protons present in the water compared to the surrounding medium, causing the energy transfer to take more time than expected. This is why water takes a long time in the process of recovery. The difference in frequency of the protons rotating in the water compared to the protons in fats is that if I have a 1.5 Tesla machine at 220 Hertz, the greater the magnetic field, the greater this difference slightly becomes. That's why it is important. Fats have a short T1 value, unlike water, which has a long T1. So we mentioned that this difference, which is 220 Hertz, refers to the difference between the protons that are rotating. Look at that. The difference in water? Excellent. The difference between water and fat. What is this difference? It is said to be 3.5 times 10 to the power of minus 6 parts per million. 1 million means parts per million. That's why we multiplied by 10 to the power of 6. He told you that if you hit the arm frequency to know what this value transforms into, I calculate the chemical shift, which is the difference in frequency between the protons rotating in water and the protons rotating in fats, which is approximately 220 Hertz. This is between water and fats if I'm working at about 1.5 Tesla. Okay, if I increase the Larmor frequency, I will have increased the machine's magnetic force to 3 Tesla, which would be 440 Hertz. The more you increase the magnetic field strength, the more you increase the chemical shift between fats and water. You might find yourself working on an open device and asking it to perform a fat saturation sequence. It may or may not work because fat saturation relies on the chemical shift phenomenon. You need a high magnetic force or high magnetic strength device to maximize the difference between fats and water in frequency, so you can work on the sequence as we will. Explain shortly. Well, no, thank you very much indeed, really. Beautiful. Do you want to understand this danger? I will see, beautiful like, thank you. What kind of image is this, doctors? This is a STIR sequence image. It's neither T2 nor T1 nor proton density. This image is called STIR, which is a type of sequence. Now pay attention. The journey started to evolve, and the inventors of the imaging technology began to think, what should we do? So they said, let's play around with this. We understand the method, we understand the world, and we understand the work. Let's create something based on the differences between the various tissues in our magnetic field properties. So, what does this mean? This image, if you look closely, shows the muscle and fat. Here is the detailed investigation of the average investigation. In this image, if you pay attention, you can see the fat. And here is the muscle, which is darker than the areas that contain fluid. For example, in this image, you will find it clearer, perhaps even more so. Here, you have the fluid appearing very bright and the fat appearing dark in your image. This is very clear in the Belv's area. So what happened in this image is that I made the fat signal and most of the tissues dark, meaning I applied a suppression technique to weaken it significantly. This allowed the signal from the fluid or water-containing tissues to appear very prominently in the image. Now, how did I achieve this? It's the same idea we were discussing, but instead of giving 90 and 180 degrees, you apply something called a saturation pulse, of 180 degrees before the 90 and 180 degrees. What this means is that I have fat, water, and other tissues present. When I place the patient inside the magnetic field, all the protons aligned